Welcome to today's session. In this video, we will tackle LeetCode problem number 1835, find XOR sum of all pairs bitwise and. This is a fascinating problem that combines bitwise operations and array manipulation, giving us an opportunity to explore both mathematical intuition and efficient algorithms. Let's dive in. In this problem, we are working with two integer arrays, ARR1 and ARR2. The goal is to calculate a specific value called the XOR sum of all pairs bitwise and. Let's break this down. First, the XOR sum of a list refers to the result of applying the bitwise XOR operation to all the elements in that list. If the list happens to be empty, this XOR sum will default to 0. Now, the XOR sum of all pairs bitwise and is a bit more involved. It is calculated by taking every possible pair of elements from the two arrays, applying the bitwise and operation to each pair, and then computing the XOR of all these results. Finally, we are tasked with returning this computed XOR sum as the answer. The input format specifies that both arrays have lengths between 1 and 30,000, and their elements are non-negative integers less than or equal to 1 billion. The output is a single integer representing the XOR sum of all pairs bitwise and. To make this problem clearer, let's walk through an example. Suppose ARR1 is 1, 2, 3, and ARR2 is 6, 5. To calculate the XOR sum of all pairs bitwise and, we start by examining every possible pair between the two arrays. For the first element of ARR1, which is 1, we compute 1 and 6, which equals 0, and 1 and 5, which equals 1. Next, for the second element of ARR1, which is 2, we compute 2 and 6, resulting in 2, and 2 and 5, which gives 0. Finally, for the third element of ARR1, which is 3, we calculate 3 and 6, which equals 2, and 3 and 5, which equals 1. For now, we have a list of results 0, 1, 2, 0, 2, and 1, obtained from all possible pairs. The next step is to compute the XOR sum of all these values. When we apply the XOR operation sequentially to the list of results, we get 0 XOR 1 XOR 2 XOR 0 XOR 2 XOR 1. Performing these operations step by step, the final value comes out to be 0, which is the answer for this example. To further solidify our understanding, consider a simpler case where ARR1 is 7 and ARR2 is 3. Here, there's only one pair to consider, 7 and 3, which equals 3. Since there's only one result, the XOR sum is simply 3. This demonstrates how the problem can be straightforward when the arrays are small or contain only one element. Now, let's explore another example. Suppose ARR1 is 4, 3, 8, and ARR2 is 1, 2. Here, we compute the bitwise and for all possible pairs. For the first element of ARR1, which is 4, we calculate 4 and 1 is 0 and 4 and 2 is 0. For the second element of ARR1, which is 3, we compute 3 and 1, which equals 1, and 3 and 2, which equals 2. For the third element of ARR1, which is 8, we calculate 8 and 1 is 0 and 8 and 2 is 0. This gives us the results 0, 0, 1, 2, 0, and 0. Finally, taking the XOR of all these values, we get 0 XOR 0 XOR 1 XOR 2 XOR 0 XOR 0, which simplifies to 3. This means the answer for this example is 3. These examples illustrate how the XOR sum of all pairs bitwise and is computed step by step. When solving this problem, there are a few edge cases to consider. First, if both arrays consist of a single element, such as ARR1 equals 1 and ARR2 equals 1, the output should handle this simplest scenario correctly. Another edge case is when both arrays contain only zeros, like ARR1 equals 0, 0, 0, and ARR2 equals 0, 0. Since all pairs will evaluate to 0, the XOR sum will also be 0. For larger inputs, where arrays have the maximum number of elements and values, efficient computation is critical to ensure the solution runs within the time limits. Additionally, if the arrays have unequal lengths, such as ARR1 equals 2, 4, 6, and ARR2 equals 1, 2, it's important to ensure that all pairs are correctly accounted for in the computation. By considering these edge cases, we can ensure that our solution is robust and handles all scenarios effectively. To solve the problem of finding the XOR sum of all pairs bitwise and between two arrays, we can consider several approaches. The most straightforward one is the brute force method. Here, the intuition is simple. We iterate through every possible pair of elements from the two arrays, compute their bitwise end, and maintain a running XOR of all these results. While this approach is conceptually easy, it involves a nested iteration across both arrays. For arrays of sizes m and n, this results in m multiplied by n pairs, leading to a time complexity of O, m*n. Let's break this algorithm down step by step. First, we iterate over each element in the first array. Then, for each element, we iterate over all elements in the second array. For each pair, we calculate the bitwise and XOR this result with our running total. For example, if ARR1 is 2, 1, and ARR2 is 3, 4, the pairs would be 2 and 3, 2 and 4, 1 and 3, and 1 and 4. The result would then be the XOR of all these values. While straightforward, this method becomes computationally expensive as the sizes of the arrays grow. Now, while the brute force method is simple to implement, it becomes impractical for large inputs, where performance is a critical concern. To overcome this, we can adopt an optimized approach by leveraging some key observations about bitwise operations and the properties of XOR. First, recall that XOR is both associative and commutative, allowing us to rearrange and group operations without changing the result. This insight helps us decompose the problem further. Instead of calculating all pairwise ends directly, we can focus on the frequency of bits set to 1 in both arrays. For instance, rather than iterating through every pair, we calculate the contribution of each bit position to the final XOR sum. Here's how the optimized algorithm works. For each bit position, from 0 to 31 for 32-bit integers, we count how many elements in the first array have this bit set to 1 and do the same for the second array. Using these counts, we can efficiently calculate the contribution of this bit position to the overall XOR sum. This drastically reduces the computational effort, as we only need to process each array once for all bit positions. The resulting time complexity is O, 32*, m plus n, which simplifies to O, m plus n, since the constant factor of 32 comes from the number of bit positions. The optimized approach stands out as the better choice over brute force because it scales efficiently with large arrays, where m and n can be as large as 10 to the power of 4. While the brute force method is intuitive and easy to implement, its O, m*n, time complexity makes it computationally prohibitive for larger inputs. The aha moment here is the realization that we don't need to compute all pairwise ends individually. Instead, by aggregating the contributions of each bit position across all elements, we eliminate redundant computations and simplify the problem significantly. This insight not only reduces the computational burden but also highlights the power of understanding bitwise operations. A quick comparison reveals the trade-offs. While the brute force method is simple, it's inefficient for larger inputs. The optimized approach, on the other hand, is highly scalable but requires a solid grasp of bitwise properties. By focusing on the optimized strategy, we achieve the best balance between efficiency and clarity, making it the ideal solution for this problem. In this problem, we are asked to find the XOR sum of all pairs bitwise in between two arrays, ARR1 and ARR2. Mathematically, this means calculating the XOR of ARR1, I, and ARR2, j, for all valid pairs of indices I and j. The naive approach to solve this problem would involve iterating through every possible pair from the two arrays and performing the AND operation followed by the XOR. However, this approach has a time complexity of O, n*m, which can become infeasible when the sizes of the arrays are large. To optimize this, we can leverage the properties of bitwise operations and mathematical insights. First, it's important to understand that both XOR and AND operate at the bit level, meaning they process one bit at a time independently of the others. This allows us to decompose the problem into smaller, manageable computations for each bit position. Additionally, the associative property of XOR, which states that a XOR B, XOR C is equivalent to a XOR B XOR C, can help us compute the XOR sum incrementally. Finally, instead of treating numbers as a whole, we can break them down into their binary representation and analyze how each bit contributes to the final result. To compute the XOR sum efficiently, we focus on the contribution of each bit. For a given bit position k, we need to determine how many pairs contribute to the kth bit of the result. This involves counting, first, the number of elements in ARR1 where the kth bit is set to 1, which we call count1, and second, the number of elements in ARR2 where the kth bit is set to 1, which we call count2. Using these counts, we can calculate the number of pairs where the kth bit of the AND operation between elements from ARR1 and ARR2 is 1. Specifically, this is given by the product count1_set times count2_set, where count1_set represents the elements in ARR1 where the kth bit is 0, and count2_set represents the elements in ARR2 where the kth bit is 0. With this information, we can determine whether the number of contributing pairs for the kth bit is odd or even. If it's odd, the kth bit contributes 1k to the XOR sum. If it's even, it contributes 0. This way, we can compute the XOR contribution for each bit position independently. After calculating the contribution of each bit, the final step is to iterate through all 32 bit positions and accumulate the results. By processing each bit from 0 to 31, we calculate the XOR contribution for that bit and add it to the total result. Once all bits have been processed, the accumulated value represents the XOR sum of all pairs and values. The key insights here are crucial for understanding why this approach is so efficient. First, the independence of XOR and AND operations at the bit level allows us to decompose the problem into smaller subproblems, one for each bit. Second, instead of directly iterating over all pairs, we use a counting approach to determine the number of contributing pairs for each bit. This drastically reduces the computational complexity. Finally, the contribution of a bit to the XOR is determined solely by whether the total number of contributing pairs is odd or even. This avoids the need for direct computation of the AND operation for every pair, further optimizing performance. With these insights, we achieve a highly efficient solution. The time complexity of this algorithm is determined by the bit counting process. For each bit position, counting the number of ones in both arrays takes O and plus m time, where n and m are the sizes of ARR1 and ARR2, respectively. Since there are 32 bits to process, the total complexity becomes O, 32 asterisk, and plus m, which simplifies to O, and plus m, because 32 is a constant. This is a significant improvement over the naive O, and asterisk m, approach. The space complexity of the algorithm is O(1), as it requires only a constant amount of additional space for counters and intermediate variables. By efficiently leveraging bitwise properties and counting techniques, we achieve a solution that is both time and space optimal for this problem. This solution efficiently calculates the XOR sum of all pairs bitwise and by leveraging properties of XOR and AND operations. Instead of iterating through every pair of elements in the two arrays, which would result in O and asterisk m complexity, we use a key mathematical insight. Specifically, the XOR of all pairs ends can be computed as the n of the XOR of all elements in the first array with the XOR of all elements in the second array. First, the XOR of all elements in ARR1 is computed and stored in XOR1. Similarly, the XOR of all elements in ARR2 is computed and stored in XOR2. Finally, the result is calculated as XOR1 and XOR2, which represents the XOR sum of all pairs ends. This approach is highly efficient, with O, n plus m, time complexity, where n and m are the lengths of ARR1 and ARR2, respectively. The code is clean and concise, with clear variable names, and handles all edge cases, such as empty arrays, by naturally returning 0 in the absence of elements, since XOR of an empty set is 0. This ensures correctness and optimal performance for all valid inputs. This is the Java implementation of the problem find XOR sum of all pairs bitwise and LeetCode number 1835. The solution mirrors the Python logic by first computing the XOR of all elements in ARR1 and ARR2, and then returning the bitwise and of these two XOR results. Key differences include the use of Java's enhanced for loop and explicit type declarations for variables. To solve this problem, we start by working through an example with ARR1 set to 1, 2, 3, and ARR2 set to 6, 5. The first step is to compute XOR1, which is the XOR of all elements in ARR1. We initialize XOR1 to 0 and then iterate through each element of ARR1. First, we XOR 0 with 1, which gives us 1. Then, we XOR 1 with 2, resulting in 3. Finally, we XOR 3 with 3, which brings us back to 0. This means the final value of XOR 1 is 0. Next, we calculate XOR 2, the XOR of all elements in ARR2, following a similar process. We initialize XOR2 to 0, then XOR it with 6 to get 6. After that, we XOR 6 with 5, resulting in 3. The final value of XOR2 is 3. Now that we have XOR1 and XOR2, we compute the result by taking the bitwise AND of the two values. Specifically, we calculate XOR1 and XOR2, which is 0 and 3. This evaluates to 0, so the final result for this example is 0. Moving on to a second example, let's consider ARR1 as 4, 1, and ARR2 as 7, 8, 9. Again, we start by calculating XOR1, initializing it to 0. First, we XOR 0 with 4, which gives 4. Then, we XOR 4 with 1, resulting in 5. Thus, the final value of XOR1 is 5. Similarly, we calculate XOR2 for ARR2, starting with 0 and XORing it with 7 to get 7. Next, we XOR 7 with 8, which gives 15, and finally, we XOR 15 with 9, resulting in 6. The final value of XOR2 is 6. With XOR1 as 5 and XOR2 as 6, we now calculate the result by performing the bitwise AND of these two values. Specifically, we compute XOR1 and XOR2, which is 5 and 6. This evaluates to 4, so the final result of this example is 4. Let's explore one more case to solidify the concept. Here, ARR1 is 0, 0, 0, and ARR2 is 1, 2, 3. We begin by calculating XOR1, starting with an initial value of 0. Since all elements in ARR1 are 0, XORing 0 with 0 3 times still gives us 0. Therefore, the final value of XOR1 is 0. For XOR2, we start with 0 and XOR it with 1, resulting in 1. Then, we XOR 1 with 2, giving us 3, and finally, we XOR 3 with 3, which brings us back to 0. So the final value of XOR2 is 0. With both XOR1 and XOR2 being 0, we calculate the result by performing the bitwise AND of these two values. Specifically, we compute XOR1 and XOR2, which is 0 and 0. This evaluates to 0, making the final result of this example 0. Through these examples, we've demonstrated the step-by-step process for computing the XOR sum of all pairs bitwise and efficiently, leveraging the properties of XOR AND operations to simplify the calculations. In terms of time complexity, the solution employs an optimized approach to compute the XOR sum of all pairs bitwise AND. First, we calculate the XOR of all elements in ARR1. Since this involves iterating through n elements, and each XOR operation is a constant time operation, this step requires n time. Similarly, the computation of the XOR for ARR2 involves iterating through its m elements, resulting in an m time complexity for this step. Finally, to compute the result, we take the bitwise AND of the XOR values obtained from ARR1 and ARR2. Since a bitwise AND between two integers is a constant time operation, this step takes 1 time. Together, these steps form the foundation of the solution's time complexity. Now, combining the time complexities of all the steps, we get n for RR1, m for RR2, and 1 for the final computation. Adding these together gives us an overall time complexity of n plus m. Shifting to space complexity, the input arrays ARR1 and ARR2 are provided as input and do not require additional space beyond their original storage, which is n plus m. For auxiliary space, we only use two integer variables, XOR1 and XOR2, to store intermediate results. These variables consume constant space, 1. No additional data structures are used, so the overall auxiliary space complexity is 1, excluding the input storage. To put this into perspective, let's compare the optimized approach with the brute force method. The naive brute force approach involves iterating through all pairs, A, B, where A is from ARR1 and B is from ARR2. Since there are n*m pairs, and each pair requires constant time operations to compute the bitwise AND an XOR, the time complexity of the brute force approach is n*m. However, it only requires 1 auxiliary space. In contrast, the optimized approach eliminates the need to compute all pairwise results explicitly by leveraging the mathematical properties of XOR and n operations. This reduces the time complexity to n plus m, while maintaining an auxiliary space complexity of 1. The efficiency of the optimized approach is grounded in the distributive property of XOR over AND. Using this property, the XOR of all pairwise A_I and B_J values can be simplified to XOR of ARR1 and XOR of ARR2. This eliminates the need for explicit pairwise computations and leads directly to a linear time complexity relative to the input sizes. Furthermore, this approach ensures consistent performance across all cases. Whether the input arrays contain large or small values, the best, average, and worst case time complexities remain O, n plus m, as the solution relies solely on linear traversals and constant time operations. This makes the approach not only efficient but also robust and predictable in its execution. When tackling this problem, there are a few common pitfalls to be aware of. First, using brute force for large inputs is a major mistake. Brute force involves iterating through all possible pairs of elements in ARR1 and ARR2, calculating the bitwise and for each pair, and then XORing the results together. While this approach might be acceptable for small datasets, it has a time complexity of O, n squared, which becomes impractical when the size of the arrays exceeds 10 cubed or more. Always analyze the time complexity of your approach before implementing it. Another frequent error is misunderstanding the properties of XOR. Remember, XOR is associative and commutative, meaning the order in which you perform the operations does not affect the result. Misinterpreting this can lead to overly complex or even incorrect implementations. Finally, failing to recognize opportunities for optimization is another common issue. For example, taking advantage of patterns in bitwise operations, like knowing that the AND operation with 0 always yields 0, can help simplify calculations. Pre-computing results for frequently occurring numbers is another way to reduce redundant computations and improve efficiency. Additionally, incorrect handling of edge cases can cause problems. For instance, if one or both of the input arrays are empty, the XOR sum should naturally be 0. Forgetting to account for this scenario can lead to runtime errors or undefined behavior. Another common issue is confusing the operations of bitwise and in XOR. It's essential to compute the bitwise and for each pair of elements first and only then XOR the results together. Mixing up these operations can lead to incorrect outputs and a fundamental misunderstanding of the problem requirements. Now, if you're solving this problem in an interview setting, it's important to approach it with a bit-level mindset. Many problems involving bitwise operations require you to identify patterns in the binary representations of numbers. For example, the presence of a 1 at a given bit position in both arrays determines its contribution to the final result. Pre-computation can also be a powerful tool. For instance, counting the frequency of bits in the arrays ahead of time can simplify the calculations significantly. Lastly, during interviews, make sure to communicate the trade-offs of your chosen solution. For example, if you optimize from O, n squared to O, n, explain why this change was necessary and how it improves performance. This demonstrates your ability to critically evaluate and refine your solution. Now, let's consider related problems and alternative approaches. If you're interested in exploring similar challenges, there are several relevant problems on LeetCode, such as XOR queries of a subarray, count triplets that can form two arrays of equal XOR, sum of all subset XOR totals, and counting bits. These problems help build a stronger understanding of XOR operations and their applications. As for alternative approaches, one efficient method is the optimized frequency-based approach. Instead of iterating through all pairs, you can count the frequency of each bit in ARR1 and ARR2. Using these counts, you can directly compute the XOR sum without explicitly iterating through every pair. This reduces the complexity to O, 32*n, where 32 is the number of bits in an integer. While this approach does require additional space for storing frequency arrays, it is significantly faster for large inputs. Another creative approach is divide and conquer. By splitting the arrays into smaller subproblems, you can compute partial XOR sums and then combine the results. Although this method may not be the most efficient, it demonstrates ingenuity and a different way of approaching the problem. Finally, let's discuss some bit manipulation tricks and key takeaways. Bitwise masks can be used to isolate specific bits, allowing you to calculate their contributions in bulk. This often involves clever use of bit shifts and masks to optimize computation time. For example, you could use masks to focus on specific bit positions and avoid processing irrelevant bits altogether. As you work through problems like this, always analyze the problem for patterns in bitwise operations. These patterns can often reveal opportunities for simplification or optimization. Pre-processing or frequency-based methods, such as counting bit occurrences in advance, can significantly reduce the complexity of pairwise calculations. Lastly, it's crucial to carefully handle edge cases. Validate your solution with small, simple test cases to ensure correctness before scaling up to larger inputs. By keeping these principles in mind, you'll be better prepared to tackle variations of this problem efficiently and effectively. Great job! We've successfully solved the problem by combining bitwise operations with mathematical insights. Remember to practice similar problems to strengthen your understanding of XOR and NAND operations. Thanks for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!